Hello, this is Mr. Collier, and today we're going to be looking at maximums and minimums of functions. Alright, so uh, basically if we have a maximum, we'll have the derivative will be positive, then the derivative will be negative, and in the middle somewhere we have a maximum where the derivative is equal to 0. So we can find out where the derivative is equal to 0, then we'll have we'll possibly have a maximum or a minimum. Okay, so we have to look for the stationary points in a function, also called turning points, and then figure out if they're a maximum or a minimum. So here's some steps to follow. We're going to do that for this function on this interval. So find the greatest or least value of this function. So first let's find the derivative. So dy by dx equals 3x squared minus 12x is the derivative. Then we're going to make the derivative equal to 0. That's finding stationary points. That's how we find out where the stationary points are. Alright, so step 2, 0 equals 3x squared minus 12x. We can solve this algebraically. We can also solve it with the calculator. Let's try that method. So we can use polysmalt 2. And let's enter here. Next. Alright, so we put in 3, because we have 3 in front of the x squared, then negative 12. And there's no c value here, so let's just put in 0 for c, and then solve, and we get 0, 4. So we get x equals 0, and x equals 4 are the stationary points. So we solve for x. We can graph the function to decide whether they're a minimum or maximum. So remember, I'm going to graph the original function to see what it looks like. For the window, I can do zoom 6. I can actually use this interval right here if I need to. Well, let's just see what it looks like with zoom 6 first. Okay, so here's what the function looks like with zoom 6. I'm actually going to change the window settings so that I just see these x values here, and maybe make the y min a bit lower so I can see the minimum here. So I'm going to change the x min to negative 2 and the x max to 5 and y minimum, I don't know, negative 30 maybe. Okay, so now I can see most of the function. I can see this minimum right here. So when we're checking for the greatest and least value of the function, we'll need to check a couple of things. We'll need to check the stationary points, and we also have to consider the endpoints. Okay, because you may have maximum or minimum right here. If you look at the graph, this is just a local maximum and a local minimum. Later on in the function, we'll have values bigger than this maximum. So it's only a local maximum and local minimum. Then you'll have to check the endpoint. So I'm going to definitely check this endpoint over here at x equals negative 2, because it looks like it might be as low or lower than this minimum. So that will be the minimum value of the function on this interval. But it doesn't look like I need to check the point over here at x equals 5, because that's definitely lower than the maximum. So this is definitely the maximum on this interval. And we got the stationary point before as x equals 0. So at x equals 0 we have a maximum. So for number 4 here, we have a greatest value. Greatest value at x equals 0. And we have to find the greatest value, so we can just put 0 into the original function to find the y value. We can also get the values on our table. Okay, this is particularly handy if you have many values to get. So we look at the table at 0, the y value is 5. So 5 is the maximum value on that interval. And now we're going to find the least value. Alright, so we're going to check that stationary point, x equals 4. Okay, so if I look at the graph over here, we have a minimum, and then I'm going to check this endpoint over here as well at x equals -2. So I'm going to check both of those. Now you can work it out using the original function, but I can use the table to get both of them right away. So second function table, and we have at -2 the y value is -27, and at 4 the y value is -27. So it's the same thing. Okay, we have the minimum value at both these spots, but the minimum value of the function is -27. So we're going to be finding some maximums and minimums for some word problems now. So we have to model some situations with an equation and then do the steps we just did to solve the problem. Got a bunch of steps here listed. We're going to go through them all for a very common example where you're trying to maximize an area of a rectangular region. Okay, so in this case we have a rectangular field is bordered by a straight canal and is enclosed on 3 sides by 120 centimeters of fencing. So this is a fence. It's in total 120 centimeters. Find the maximum possible area of the field. The maximum possible area. So you need to make an equation. We need one variable. We can call this x or w and l for the width and the length. But that's not going to work with 2 variables. We need one variable, and the key is that the whole thing here has to add up to 120. Okay, so if we call the width x, okay, so we'll say the width equals x, and the length will be, we have x plus length should equal 120. So the length should be equal to 120 minus 2x if I subtract these 2x's from both sides. So here we have the length is 120 minus 2x. So that's your first goal, is to get everything in terms of one variable. Identify constraints. I guess we have to say that here x has to be, of course, greater than 0, and 120 minus 2x has to be greater than 0. We might have to check our answer with these constraints afterwards, maybe, possibly, sometimes. Establish a model function. So that's a function like y equals some function of x. We're talking about area here. We want to find the maximum area, so I'm going to say area equals, well, it's going to be length times width, right? So it's x times 120 minus 2x. Alright. Well, let me simplify that in case we need it to. 120x minus 2x squared. Okay, so the next steps, we don't really necessarily need to do them right now because we've got our function, which is what we want, and it's already solved for one variable. We already have a function area equals 120x minus 2x squared, so we don't need to follow those other couple steps. We've got a function. We'll be able to find a derivative and find the maximum. So we can do this without GDC and with GDC. So first of all, the formula is 120x minus x squared. So area equals 120x minus 2x squared. So if I find the derivative, we call it dA by dt, or dx, is 120 minus 4x. Make the derivative equal to 0 and solve. Okay, so we'll solve this. We'll have 4x equals 120 divided by 4, x equals 30. So we have maximum area at x equals 30. So recall in our diagram, this was x, and this is x, and this is 120 minus 2x. Or, well, remember that our equation was area equals 120x minus 2x squared. So we can just put in the x equals 30 and find the area when x equals 30. Alright, so I can work that out by hand or work that out on the calculator. And we've got 120 times 30 minus 2 times 30 squared. Okay, and that gives us 1800. So 1800, I forgot the units, maybe it's square meters, is the maximum area. Oh, centimeters. So the maximum area is 1800 square centimeters. We could have also done this with the GDC. You can graph the function. So I can type in the original function, not the derivative, 120x minus 2x squared. And maybe I'll go to zoom 6. Actually, zoom 6 probably won't work because my maximum area is going to be huge. It's going to be up to 1800. So the x max may be 40. Okay, I already know the answer, so I know what to type in here, but you just have to kind of fiddle around with it if you don't already know the answer. But I should be able to see the maximum when I had the window settings like this. Okay, so there you can see the maximum is right here, and we can go to second function trace and go to number 4. Oops. Alright, so left bound, then I'll go to the right of that maximum and press enter. So you can see here the maximum is at x equals 30 and it is 1800 square centimeters. So you can do it without the GDC or with the GDC. Pay close attention to the instructions. It might require to use find the answer using the derivative, and then you'll have to do it by hand.